All right, so in this tutorial we are going to get our first introduction to a fundamental force of nature, magnetism. We're all familiar with magnets, especially associated with toys and putting pictures up on a refrigerator. This tutorial is going to focus on actually very difficult to understand, at least historically, aspects of permanent magnets. Our focus really for this chapter is going to be on electromagnetism. But we want to have kind of like a baseline to understand what magnetism look like, and we're going to introduce the idea of fields. So we're not going to spend much practice with this, but it's an important baseline for which we're going to start. So I mentioned earlier that magnetism is a fundamental force. There's lots of forces in nature, only a few are fundamental. And in fact, magnetism isn't even fundamental itself. It's part of a more fundamental force, something we'll worry about later in the year. So let's start by reviewing what we already know. We already know gravity is a fundamental force, electricity. Now we're adding to that magnetism. So we can ask some very basic questions. First of all, if gravity is going to act on something, what property do we have to have? Okay, so gravity is caused by and acts on what property? Well, we know that's mass. What does electricity act on? Well, we think about it, it's charge, a completely different property than mass. Gravity is always attractive. That's what I mean by direction. Okay, electricity is either attractive or repulsive. I'm not going to write those out. So now we're coming to magnetism. Imagine you have a metal bar. We know most magnets are made of some metal. What makes that metal bar magnetic as opposed to just being a non-magnetic metal bar? There's nothing obvious about that question. There's no special material in there like magnesium or magnetismium. It's something about the atoms themselves. Okay, so we're going to explore this much greater, but I'm just going to give you the short answer here. Magnetism ultimately is due to moving charges. Okay, and there's another way. There's two different ways to look at this. Moving charges, and there's another fundamental property that charged particles have besides charge and mass, and that's something called spin. So depending on the situation, we can look at this fundamental property called spin, which all electrons and protons have, which make them tiny little magnets. But in a more macroscopic sense, it's this idea of moving charges, usually electrons. And so that's going to be the theme for really much of what we're going to do in this chapter. And magnetism, like electricity, is attractive or repulsive. Okay, so we will come back to that fundamental stuff a little later on. So let's take the first case, the one we're most familiar with, but really the most difficult to understand, and that's called permanent magnets. Okay, those are the magnets you have with your toys or use on a refrigerator. It's a material that stays permanently magnet. Okay, and to understand how a permanent magnet works, and here we have representations of a magnet versus a bar of iron, is if, I'm going to look at these things. If we were to take the macroscopic material and break it into little regions, and I've just randomly done them here, and in actuality they'd be much smaller than this. All right, we call those regions domains, not to be confused with domain from mathematics. And each domain acts as a tiny magnet pointing in a certain direction. Why? Well, ultimately because if you have the atoms, and in the atoms you have electrons that have their own spin and they're zipping around the nucleus, they are moving charges. So essentially all the atoms act as tiny magnets. It's just that within a certain domain they all work in concert and point in the same direction. So if you take a regular bar of iron, this domain in the upper left hand corner, all the magnets might point in that general direction. Whereas in the lower left hand corner they might point this way. And if I continue on, I'm just going to draw a bunch of random arrows. As best as I can do random. All right, and I hope you see where I'm going with this. If I add up the net result of every domain, I essentially get zero, no overall magnetic field. Whereas in a permanent magnet, you can guess that the domains essentially are very well aligned. The more aligned they are, the stronger the magnet. So again, each domain is a region of atoms pointing in the same direction, magnetically speaking. And when you put them all together, you get up all those vectors, if you will, and you get a much stronger magnet. Now the question is, well, how do you take a bar of iron and make it magnetic? How do you align those domains? Well, you need a magnetic field. And that almost leads to a chicken and egg type problem. How do you create a magnetic field without a prior magnetic field to align your domains? That's a question we'll address later on. Okay, so certain aspects of this, and I'm just giving you some factoids, hopefully they don't seem too random here, is imagine you have an iron nail and you bring it in contact with a magnet. Okay, now I'll demonstrate this in class. Unfortunately, I can't demonstrate it to you right now. But imagine I bring that nail up to the magnet, it's going to be attracted. Then if I bring up other non-magnetic materials, let's say paper clips, at the tip of the nail will also attract and pick up a few of those paper clips. So I have, if you will, I've got a magnet, then I've got a nail, and then I've got a bunch of paper clips hanging from that nail. Okay, you've probably seen something like that before. So the question is, how is this nail able to hold on to those paper clips? Well, it's not that the magnet is acting over this distance, because we'll learn that it grows weakly very quickly. It's that the magnet is influencing the domains of the nail. And the nail has now become temporarily magnetic. Temporarily. So here we're using the magnetic field of a magnet, I'll just label this, to temporarily make this magnetic, and it picks up the paper clips. And then you can imagine if I take the magnet away, the nail does not retain its magnetism. That's why it's temporary. Okay, so there we can align the domains fairly well, but we don't lock them in. Generally, if you want to lock them in, you want to start with a molten version of the metal and then expose it to a magnetic field, and then when it cools, that will lock it in. But we don't have to worry about that. All right, what kind of materials respond to magnets? Generally metals, but not all metals. Some metals actually make magnetism weaker, some make them stronger. There's terms to that, paramagnetism and diamagnetism. I'm not going to get into that, but here are the metals that you want to be aware of. Iron is definitely a big one. Okay, iron and certain minerals that are iron-based. There are certain alloys. A common one is Al-Ni-Co magnets. They're alloys of aluminum, nickel, and cobalt. So those are some of the cheap magnets. And perhaps the strongest magnets you can get per size are rare earth magnets, usually made of neodymium. Okay, I'm not going to quiz you on this, but it's just a little FYI. And then next question, what property do all magnets have? Well, what property does matter have? We would say mass. What property do charges have? We'd say charge. What property do magnets have? We'd say there's polarity, okay, as opposed to charge. And an important point, all magnets must have a north and south pole. Okay, so I'm going to step back a little bit for a second. So going to the idea of electricity, that's what I meant to say. All electrical objects have a property called charge. And it can be either positive or negative, or you can have both. An electron is all negative. A proton is all positive. A metal sphere has equal numbers of positive and negatives. Magnets are different. They don't have charge associated with them. They have poles associated with them, polarity. And every magnet must have a south and a north. You cannot have a magnet that's all north or all south. It's fundamentally impossible. Okay, so you want to keep that in mind. And it doesn't hard to figure out. You probably know this, that like poles will repel and opposites attract. Okay, just like positive and negative charges, north will attract the south, a south will repel a south. All right, now we want to start mapping out fields. If we have a magnet or a series of magnets and we want to understand what does the field look like, we want to look at magnetic fields as opposed to electric field. And by the way, magnetic field is called a B field. I'm not sure why B, but it is what it is. Okay, so how do you actually map out a field? That's not too hard. Much easier than an electric field. We can use a compass. Hopefully you've all seen compasses before. So I'm going to teach you the rules of compasses and then we'll show that. So the rule is a needle always points away from the north magnetic pole and therefore toward the south magnetic pole. So I have a simple schematic of a magnet here, north pole, south pole. These circles represent a compass. And so if I were to place a compass to the left of the north, by the rule, the needle would point away from the north. And as we move it to the south, we would have to point toward the south. Okay, we will learn in a minute, what if we put the compass right there, which way would it point? Spoiler alert, it would point this way. Okay? Now, you might be thinking, wait a second, didn't I hear at some point in my life that compasses point towards the north? And I'm telling you right now, they point away from north. Well, we're confusing two types of poles. Again, this is just FYI stuff. So if this right here represents the Earth, and this represents the axis about which we rotate, right here where Santa Claus lives is the North Geographic Pole. All right, and where the penguins live down here is the South Geographic Pole. What we're talking about are magnetic poles. It just turns out at this time in our history, not far from the North Geographic Pole is the South Magnetic Pole. I know it can be confusing, and over here would be the North Magnetic Pole. So if I have a compass somewhere on the Earth here, it's going to point this way towards the North Geographic, but because of the South Magnetic. All right, so give yourself time to digest that. All right, now let's look at what the field lines surrounding permanent magnets look like, and they have three different situations. So I'm going to show you a little applet right now to kind of give you an idea, and then we'll go from there. All right, so here is just a generic bar magnet, north and south pole, and here is a compass. And notice that the compass, the red is pointing away. That's the needle right there. Okay, that's the needle. So if I move it to, let's see if I can click and drag this, over here, notice that it's starting to, the red part is pointing like an arrow to the south. And if I move it somewhere between, come on now, notice that it's parallel pointing kind of toward the south and away from the north. And if I follow this carefully, notice it starts dipping. And if I trace backwards and I'll follow the white, you can kind of see that there is a loop forming around that pole. Okay, and if I go underneath the magnet, notice again I'm going from south to north. If I follow the white, it's pointing away. Now we're going backwards. So I see we get another loop. Okay, long story short, what would that translate to that? Actually, let me go back to this. If I show the actual field lines, okay, that's what it looks like. Let me make it a little bit stronger so this shows up maybe a little bit better. Notice that the compass needles, look at the red, they form loops surrounding the magnet, always pointing away from the north toward the south. And that's going to be a common theme here. All right, so let me draw that here very, very quickly. So I start at a north, I loop around to a south. Put an arrowhead north to south. Go underneath it, do the same thing. And then as I get further away, the loops get further apart. And again, like field lines, electric field lines, they never ever cross each other. I know my resolution isn't the greatest here, and it looks like they cross, but they're not supposed to. So there's a very simple representation. And then along this axis, it kind of goes out to infinity, but it ultimately should, oops, I got the arrowhead wrong there. It should eventually loop around. So if I start at the North Pole, it goes out to infinity and kind of comes back around to the north. All right, not much more to say about that. So now we can look at combinations of magnets, and I got to rush here. So what if I put two magnets near each other? Here we have north end here, south end here. Well, we know they're going to attract because opposite poles attract, so the field line should reflect that. So one would expect the field to go from north to south, and then as we move off that, it kind of loops. And then if I go a little further away, I get something like that. Okay, and always north to south, and then this north pole might, okay, this has got to go away, and that would actually come back to that south pole. And this would kind of do something maybe, well, I take that back that way. That would be the case. That's silly. This north would more likely go to that south. Okay, but what we're interested in is the region between the magnets, and there we see attraction. Lastly, if we have like poles north and north here, we expect repulsion. So like two charges of the same sign, we're going to get repulsion. So this should be somewhat familiar to us. If I start here, I might actually have this loop around to the south very, very sharply. And we see a pattern developing here, besides the shape we expect from repulsion, is that field lines always, this is a critical point here, if they start at a north, they must end up at a south somewhere. Okay, so unlike an electric field line where a line can go out to infinity and never come back, B fields always form loops. Always. From north to one magnet to south of maybe another magnet. Okay, my time is up. Do the practice page after this, and we'll talk about it in class.